This video will introduce the 7th part of the series for basic knowledge of spectroelectrochemical method, the 4th part of optically transparent thin layer spectroelectrochemistry. This article continues to introduce the non-ideal behavior of the Nernst plots. In the previous article, the items 1 and 2 were introduced. This time the below 3rd and 4th items will be introduced. The previous discussed cases are all cases where the spectra of electroactive substances overlap, and the following case will be discussed when only one substance has light absorption. A. For backward reaction, EC mechanism. The EC mechanism is illustrated below, when the substance A undergoes an electron transfer, immediately followed by a chemical reaction. Since the total concentration of substances is constant, the sum of the concentrations of substances A, B, and C during the reaction is equal to the total concentration C**. The equilibrium constant of the chemical reaction equation 7.2 is. Substitute equation 7.4 into equation 7.3 to obtain equation 7.5. The Nernst equation 7.6 of the electrochemical reaction equation 7.1 can be written as equation 7.7. If only substance A has light absorption at the detection wavelength, the above equation can be rewritten as equation 7.8 expressed in terms of absorbance instead of concentration. The Nernst plotting is also a straight line, and the electron transfer number n can be found according to its slope, but its intercept is. From which the equilibrium constant K of equation 7.2 can be found. For the EC reaction mechanism, if only one substance has light absorption, the reaction electron number can be obtained by spectroelectrochemical measurements, and the reaction equilibrium constant can be found from its intercept. B. For forward reaction, CE mechanism. When an electron transfer is only possible following some chemical step, it is referred to as a CE mechanism. If the change in absorbance of substance B is monitored, the expression of its Nernst equation is. The slope of the Nernst plot is different from the equation potential of equation 7.9 when the equilibrium constant of the preceding reaction is small. If the equilibrium constant is large, that is, K is larger than 1, the effect of the preceding reaction can be ignored. For these systems previously mentioned, which affect only the equilibrium concentrations of reactants and products, but not other electrochemical reactions, it is still possible to obtain n from the slope of the Nernst plot, but its intercept does not correspond to its equation to measuring the potential. C. Electrode process with two consecutive electron transfers, EE mechanism. For the electrode process containing two consecutive electron transfers, already discussed in the previous article, 6th part of this series. When equilibrium is reached at potential E, there is. If only substance O produces light absorption, that is, delta equal 1, we can obtain. Where P is equal an exponential of the potential difference. Since P varies with potential, the Nernst plot is not a straight line. The Nernst plots are generally nonlinear for such systems where the presence of other electrochemical processes affects the equilibrium concentration of the monitored substances. D. For EC mechanism. When the product of an electron transfer takes part in a chemical process resulting in a molecule that can undergo another electron transfer. The expression of its Nernst equation can be obtained as. The Nernst equation can be written as. Where P is equal an exponential of the potential difference. Also, because P varies with potential, the Nernst plots are not linear. The Nernst plots are generally nonlinear for such systems where there are other electrochemical processes that affect the equilibrium concentration of the monitored substances. Consider the thin layer cell containing only the oxidizing substance O at the beginning. The initial concentration and the initial absorbance of the solution is expressed by equation 7.19. Before the deposition of the product, when E gradually becomes negative, oxidizing substance concentration gradually decreases and the reducing substance concentration gradually increases, which conforms to the Nernst equation. The material balance of the relationship equation is expressed by equation 7.20. When the potential reaches ES, Cr is equal to the solubility product Sr of substance R. When the potential steps to a more negative potential than ES, the concentration of O adjacent to the electrode surface will continue to decrease, and some of the reduced material R will be deposited on the electrode surface, because the concentration of R on the adjacent electrode surface cannot exceed SR, and at equilibrium, its concentration can be expressed by the Nernst equation as 721. Therefore, when E exceeds ES, CO decreases, but CR remains constant for SR, so when E is larger than ES, the absorbance is expressed by equations 722 and 723. Where theta E is expressed by equation 723. At the potential of E equal ES and CR equal SR, we can get the equations 724 and 725. At a potential of E smaller than ES, then we have the equation 726. If it is assumed that the reduced substance is deposited on the electrode and does not produce light absorption, which can be achieved by using a mesh electrode, we have when E tends to infinite, and the absorption can be expressed as equation 727. Combine the above equations. This gives us the below. Equation 728, for E bigger than ES. And equation 729, for E smaller than ES. Where R, E and F are as shown in the equation 730 and 731. Or for E larger than ES, it is expressed in the equation 732, where X is proportional to the oxidized and reduced species extinction coefficients. With a larger value of E, the equation 732 approaches a straight line. In the E versus ln-Re plot, the slope of this asymptotic lines gives the value of n. The intercept on the E-axis at ln-Re equal 0 is given by equation 735. When E is smaller than ES, the equation 736. As E becomes very negative, so that in the equation 736 also approaches a straight line. And, the slope of the straight line is the same as in equation 734, and the intercept at ln-Re equal 0 is expressed in the equation 738. Therefore, if the oxidized and reduced species extinction coefficients are known, the values of E0 line and F can be obtained from the above two intercepts. When epsilon R equals 0, the equation 732 can be simplified as expressed in the equation 739. The intercept and slope directly give the values of formal potential and number of electrons, and the horizontal distance between the line and the asymptote of equation 737 is minus lane of F. Figure 7.1 shows the absorption spectra of 2.36 mmol per liter of the dye and 0.4 mol per liter potassium chloride aqueous solution at different applied potentials, with an absorption maximum at 368 nanometer for the oxidized state, which also shows that dielectric constant reduction equals 0. That is, there is no absorption in the reduced state, but only in the oxidized state. Figure 7.2 shows E as a function of ln-Re. The experimental points measured at a wavelength of 368 nanometer are indicated by cross. The solid lines are the theoretical curves of equations 733 and 736. The potential pair ln-Re was plotted using the absorbance value at 368 nanometer, and the measured potential of minus 1.014 volts, SR equals 0.35 millimole per liter, C asterisk equal 2.36 millimole per liter. The dashed line is the asymptote of equations 734 and 737. This concludes the 7th chapter of the series on the basic knowledge of the spectroelectrochemical method, the 4th part of optically transparent thin layer spectroelectrochemistry.